Hello, good morning to all of you. Today, title of my talk is Thermoelastic Interaction with Memory Dependent Derivative at State Space Approach. So before we talk about some introduction, classical thermoelasticity, which is in the year 1838. So there are some drawbacks of the theory, and because the heat waves propagate with infinite speed, and first heat conduction equation does not contain any elastic term. To modify that models, several theories have developed. So classical coupled thermoelasticity, that was in the year 1956 by Biot. They have taken care of the first paradox, that is heat waves does not contain an elastic term. But in this case also it propagates with infinite speed. Next, Lord-Solomon model, they have modified the Fourier law by introducing a term known as thermal relaxation parameter in the year 1967. Next modification was in 1972 by Green and Lindsay. And relevant theoretical developments of the subject were made by Green and Lindsay in the year 1992-93. And they have in their model the temperature rate term is absent in model 2, and these models are very important. And in presently, that is in the year 2007, Professor Rai Chaudhary has developed three-phase lag model. They have used a three-phase lag parameters tau q, tau t, tau nu. So my problem, according to my problem, the formulation of the problem is we consider a thin semi-infinite piezoelectric body with a stress-free boundary. At the near end of the body, a thermal effect is given which raises the temperature of the end prescribed temperature with known function, the direction of the piezoelectric being parallel to the x-axis, and there is no free charge. We consider one-dimensional disturbance of the medium, and in our case, after non-dimensional, free from non-dimension, making our equations dimensionless, and we are arrive at the constitutive equation of motion, that is by equation 1, 2, and heat equation, that is in our case our heat equation is memory dependent derivative with three-phase lag parameter, that is by 3, equation 3. So memory dependent derivative, what is the purpose of memory dependent derivative? The main purpose is that a memory dependent derivative is functional value of real time, also depends on the past time. That is why d tau is called the non-local operator, where the integer order derivative is a local operator. And also we have used the different kernels, freely chosen kernels. Okay, and for our problem, boundary condition is sigma 0 t 0, that is stress free boundary, and a thermal load, varying thermal load is given by ft. Ft is a known function of time. Method of solution, we have applied a Laplace transformation in the previous equations, and after some manipulations we arrive at equation 5 and 6, that is second order equation in temperature, differential equation in temperature, theta bar and E bar, that is represents the Laplace transform domain, and memory dependent derivative, Laplace transform memory dependent derivative is given by 4. So we arrive at this equation after some manipulation, and equation 5 and 6 we are using to apply state space approach. So state space approach, we are writing the vector matrix differential equation by equation 7, where AS is the matrix and V bar X is given by theta bar E bar, that is the temperature and strain. And after some manipulation and after spectral decomposition and using characteristic equation method, Cayley-Hamilton theorem, all these manipulations will give the equations, most important equations in Laplace transform domain, E bar, theta bar, sigma bar, given by 8, 9, 10, strain, temperature and stress, and E1, E2 is given by these parameters. Now for numerical purpose, we have to use the Laplace inversion method. By numerically we are using the method based on Fourier series expansion technique given by Honing and Hardy's in the year 1984. For our computational purpose, we have taken the material constants as f naught is equal to 1, epsilon is equal to 0.038887, where alpha is given by beta T naught by C11, and epsilon is beta by rho Ce, where beta is the stress temperature coefficient, rho is the density, C is the specific heat. Also tau q, tau 2, tau nu, we satisfies the stability condition given in the bracket is given by 0.01, 0.02, 1.01. So we have drawn 3 diagram for theta, sigma and E. Theta represents the temperature distribution. The temperature is maximum at x equal to 0.0. We satisfy the theoretical boundary condition. Also, its magnitude in each case gradually decreases with the increase of x, which is physically possible. And number 2, And here in all the diagrams we have drawn without MDD and with MDD, that is without memory dependent derivative, with memory dependent derivative. Next, in the next diagram number 2, sigma vanishes at x.00, satisfying the theoretical boundary condition. Also you can see from the graph the steep jump of sigma occurs at a particular value of x. And also in strain we see a steep jump of particular value of x, in the neighborhood of which the strain wave shows its variation from progressive to compressive nature. Ultimately these waves dies out. So this is the comparison without memory dependent derivative and with memory dependent derivative with different kernels. So this is our small presentation. If you have any queries, doubts, please feel free to ask me or interact with me in my email and with the and I want to thank the organizer for giving me this opportunity. Thank you.